Let's take a break from all that math and let's study properties of matter. So you're sitting here in your chemistry class, and really all you've done so far is a bunch of math. That can't be right. What exactly is chemistry? Write this down now. Chemistry is the study of matter, its behavior, and its properties. By definition, matter is anything that has mass and volume. Mass is measured in grams, and volume is measured in either liters, milliliters, or centimeters cubed. There are a few key words we need to deeply understand in order to describe matter. Atoms are the building blocks of matter. You learned about atoms back in middle school, and you still need to know what they are today. They can't be broken down any further without changing the properties of said atom. Now we can take an atom, let's say we take an atom of hydrogen. So here's hydrogen. Can I break this atom down further? And the answer actually is yes. But if I break it down further, I break it down into protons that are positively charged, neutrons that are neutrally charged, and electrons that are negatively charged. When I do break it down into these subatomic particles, they no longer retain the same properties. So atoms are the building blocks of matter. You cannot break them down any further without changing their properties. Next, we have molecules. Molecules are two or more atoms joined together, acting as a unit. Let's take a look at some of the molecules in the picture above. Notice that a white circle represents hydrogen, a red circle is oxygen, and a black circle is carbon. All of these pictures are examples of molecules, two or more atoms joined together acting as a unit. Even this one here, where we have two oxygen atoms together, it's still two or more chemically combined acting as one unit. All of these are examples of molecules. Next, we have the word element. Each element is made of the same kind of atom. So look at the periodic table at the front of the room. Any element that you choose from the periodic table is made up of the same kind of atom. So all hydrogen atoms look the same, all oxygen atoms look the same, all carbon atoms look the same. And last we have a compound. A compound is made of two or more different kinds of elements. So it sounds awfully similar to the word molecule. Molecule was two or more atoms joined together. Those atoms could be the same or they could be different. For a compound, those two atoms must be different. So this molecule of oxygen that I circled before is not a compound, it's only a molecule. Compounds, those atoms have to be different. All of the other molecules pictured are also compounds. So if I look at this water molecule, for example, it is two or more different kinds of elements chemically combined. It's a compound. Same for this ethanol, and same for this really big molecule, aspirin, over here. As long as it's two or more different kinds of elements chemically combined, we call it a compound. Please make sure you have all 4 yellow words written down with good working definitions in your notebooks before we continue. Here are some great pictures to help you differentiate between the different vocabulary words you just wrote down. In red, we have atoms of an element. Atoms, the smallest part of matter that cannot be broken down any further. Molecules, two or more elements chemically combined. They can be the same element or they can be different elements. Here on the left, we have atoms of a single element. Notice that they're all the same color, all the same size, and they're not touching one another. They're not combined. Picture B, molecules of an element. Because it's the same element, it's the same color, so they're two blue spheres, and they're chemically combined, which make them molecules. I would encourage you to draw pictures along with the short descriptions below them in your notebook as well. The next picture is molecules of a compound. Recall that for a compound, we must have at least 2 different kinds of atoms. Here I have green and purple chemically combined. The different colors represent different elements, and they're chemically combined, so we can call them a molecule or a compound. The definition here says molecules of a compound. And as we move through the week, we're going to differentiate between the word pure substance and mixture. Here we have a mixture of elements and a compound. In a mixture, we have several different types of matter. Here, I have a single atom. Here, I have molecules of an element, and here I have a compound. Because they're all different substances and they're in the same container or area, we would call this a mixture. You should be able to identify each one of these vocabulary words in word format or picture format for your upcoming test. Take a look at the periodic table again at the front of the classroom. All matter is composed of only about 100 or so of those different types of elements or atoms that you see up there on that table. For example, water is made up of 1 oxygen atom and 2 hydrogen atoms. Kind of looks like a little Mickey Mouse. I'm sure you've all seen it before. So we have 1 oxygen atom, and I'll change my color here. I'll do 2 hydrogen atoms. 1 little H in there. Another little H here, and I've got a water molecule. Another example that you're familiar with is table salt, also called sodium chloride. It's composed of a sodium ion, which we'll get to later on in the year, and a chloride ion. But nonetheless, they're still elements from the periodic table. We only use about 100 or so. So what we have up there is kind of like an alphabet. We can rearrange those letters or those elements, and we make up all the different kinds of matter there are on this planet and in outer space. What is a chemical reaction? I'd like for you to write down the word chemical reaction and then the definition that follows. One substance changes to another by reorganizing the way atoms are attached to each other. The most important word that you're going to see here is reorganizing. So I'm not creating matter, I'm not destroying matter, I'm simply reorganizing the way those atoms are attached one to another. I want you to think about the way the desks are arranged in the classroom. They can be in pairs, they can be in singles, they can be in groups of 5. But regardless of the way that the desks are organized, do the number of desks remain the same? And the answer is yes. It doesn't matter if the desks are in singles or pairs or even groups of 5. The number of desks remain the same. But if I reorganize them, I form different types of groups or different types of compounds. And that's all a chemical reaction is. I'm taking one type of substance. Here on the left in this chemical reaction, we have water molecules. And I'm rearranging those different atoms over here on the right-hand side, and my products are 1 oxygen molecule, 2 or more elements chemically combined, and 2 hydrogen molecules. Notice that I have 2 red circles on the left, 2 red circles on the right. I have 4 white circles on the left, 4 white circles on the right. So all I did was reorganize or rearrange those atoms and how they're attached one to another. Matter comes in 3 different states, actually a few more than 3, but we're only going to study 3 for now. Solid, liquid, and gas. You should be fairly familiar with all 3. Now I want you to take a moment and copy down the chart you see here. I know it seems like a lot, but all of the properties that you see listed in green above on the table are very important. You need to be able to clearly and easily define all of the properties of solids, liquids, and gases on this table. So I'm going to give you a moment and copy down what you see, and then I'll highlight some of the more important properties. Let me define some of the properties for you that you see at the top of the table. First, you see volume. Volume refers to how this state of matter takes up space. Consider a solid piece of wood. What kind of space does it take up? A definite amount of space or an indefinite amount of space? And the correct answer would be definite. I could easily measure length times width times height and get a definite volume for a solid piece of metal, of wood, of plastic, of anything. What about a liquid? What kind of space does a liquid take up? If I were to pour a liquid into a graduated cylinder, which you did either last week or the week before, did it take up a definite amount of space in that graduated cylinder? The answer is yes. And last is a gas. What kind of space does a gas take up? And here our answer is indefinite. Because gases expand to take up the shapes of their containers, we say that their volume is indefinite. Shape is pretty self-explanatory, so I'm going to skip over it. Fluidity means, do those particles flow? And here's kind of my water. Do they flow one right over the other? And solid particles, they don't move at all, so they don't have any fluidity. Liquid particles easily flow one right past another, and same with gases. Although gases are a little bit further spread apart, but the particles still flow one past another. Next we have compressibility. Compressibility essentially means, can you squeeze that state of matter together? Take that solid block of wood. Can you compress or squeeze a solid? No. Can you squeeze or compress? Say this is taking up a volume here of 50 milliliters. Can I compress that liquid and make it fit into a smaller container that's, say, 10 milliliters? I know my shape isn't proportionate, but if this is 10 milliliters, can I force 50 milliliters to fit into a smaller container? Nope. Can't compress liquids. Gases, however, are easily compressible. If you take a look at the pictures over here on the far right, notice all of this empty space in between your gas particles. Because there's so much empty space between them, you can easily compress gaseous particles. Kinetic energy is how they move. Solid particles, although you may not see it or feel it, they're actually vibrating. Particles do not stop moving until we reach 0 Kelvin. And there's no way we're reaching 0 Kelvin in our classroom. Next are liquid particles. Liquid particles, besides vibrating, they also flow. So liquid particles are moving left to right, and at the same time, they're spinning one right over the other. The kinetic energy of gaseous particles, they are moving very, very quickly. So these particles vibrate left to right, they flow one right past another, and they move very quickly in multiple directions. Particle arrangement, solids are neatly packed and very close together. Draw the picture you see here. Liquid particles, they're still close packed together, but notice these little lines that you see. These lines represent fluid motion, where these particles can roll. So they're doing this little squiggly motion that I drew over here under kinetic energy. So they're close to one another, but they can flow one right past another. And then for gases, they're very chaotic. They don't have a definite pathway. They're just moving all over the place and very, very far apart. The remainder of our notes are about the differences between physical and chemical properties and changes. I would recommend that you create a T-chart of sorts, and that you put physical on one side and chemical on the other. Physical properties can be observed or measured without altering the identity of a material. Make sure you write down this definition on the left side of your T-chart. If I set down a sample of table salt, sodium chloride, in front of you, what can you observe or measure about that table salt without altering the identity or changing the table salt into a different substance? Mass, volume, color, odor, these are all examples of physical properties of a substance that I can identify without altering the identity of that sodium chloride. There are two types of physical properties, and you'll be tested on your ability to differentiate between the two. The first is called intensive physical properties. These are properties that do not depend on the amount of matter present. Here's my trick for remembering intensive. Intensive, at the beginning of the word intensive, I hear the letter N. N to me means no. So an intensive property does not know mass, does not depend on mass. So let's talk about that table salt again. So I poured out a sample of table salt in front of you. So you have this little plate, and on that plate is some salt. What physical properties? Properties that you can observe or measure without altering that salt. What can you measure or observe about that salt that does not depend on the amount that I have present? Color, odor, something like conductivity. It wouldn't matter how much I have, the property would still remain the same. What is the color of table salt if I have a small sample or a large sample? Does it change color? It remains the same. What about the odor? Does the odor change with the amount of the sample? Does its ability to conduct a current change depending on the amount I have of the sample? And its ability to conduct current, it's either a yes or a no. Can table salt conduct current, yes or no? Doesn't depend on how much I have. Ensure that you've written down the definition for intensive physical properties and several examples. The second type of physical properties are called extensive properties. Extensive properties do depend on the amount of matter present. Extensive do depend on the amount of matter present. So back to that sample of table salt. What properties are going to depend on the amount of salt that is present? Mass, volume, any measurement you would make. Say I have 1 granule of salt. If I measure its length, width, height, all of those measurements depend on the amount of matter or the size of matter that I have present. Now we're moving over to the right side of your T-chart for chemical properties. Chemical properties refer to the ability of a substance to undergo a change that alters its identity. In other words, chemical properties can only be observed when a substance is changed into another substance. A chemical reaction is a chemical change where I'm taking one type of matter and I'm rearranging it and forming a new or different type of matter. Any change in which one or more substances are converted into different substances with different properties is a chemical change. Ensure that you have this definition written down under chemical properties. You'll want to look for words like reacts with, burns, oxidizes, tarnishes. These are all examples of chemical properties, or words that would insinuate a chemical property. A few basics about parts of a chemical reaction. I'm sure you're already familiar with them from your middle school days, but on the left side we have our reactants, and on the right side we have our products. So in your examples, I would write down this here, reactants on the left, products on the right, and then 1 or 2 examples. So the first example here, hydrogen plus water, these are my reactants. I'm going to rearrange those reactants and I'm going to form the product water. So if I were to draw a picture, hydrogen only exists as a set. I would have 2 hydrogen molecules and I would have 2, or not 2, I'm just going to do 1 oxygen, and they're going to rearrange and form, I'm running out of space here, 2 water molecules. There. So now that we've talked about a physical property and a chemical property, let's talk about changes, a physical change versus a chemical change. Again, on the left side of that T-chart, a physical change is a change that alters a substance without changing its composition. So if you take this $100 bill, if I rip it into tiny pieces, it's still a $100 bill. Its properties have not changed. I may not be able to use it in the store, but as far as its properties, they remain the same. So we're looking for words like break, rip, tear, crumble. These would all be physical changes. If it's still the same thing at the end after whatever you've done to it, if it's still the same at the end, don't change its composition, we would call that a physical change. A chemical change is any change in which one or more substances are converted into different substances with different properties. And it's very important that you have different substances and different properties on your definition. Those examples are going to be the same words that we use for properties: reacts, tarnish, burns, oxidizes. Those are all great words that are evidence of chemical change. Let's take a quick example, and we've been using the water example, so I'm going to use that one. If I have hydrogen gas, if I have hydrogen gas and oxygen gas, they form water, H2O. And we'll get to balancing chemical reactions later on. We won't worry about it now. But I want you to think about the properties of hydrogen gas, oxygen gas, and water. You may not know a ton of them just yet, but let me give you a simple property to think about. Let's say you're hyperventilating and you need oxygen gas as quickly as possible. Would it be okay if they put a mask over your face that was filled with water instead? Would that have the same effect on curing that hyperventilation that you were suffering from? And it's not. Water has very different properties from oxygen gas and hydrogen gas. So when I take one or more substances and I convert them into a different substance that has different properties, I have created a chemical change. Quick quiz, let's see if you get it. Identify if the following are physical or chemical changes. Breaking a pencil in half. I see this word here, breaking. If I break a pencil in half, is it still a pencil? Does it still retain its properties? It does. This is a physical change. Leaves burning. Can I go back? After those leaves are burned, can I go back and have the original leaves that I started with? I can't. Anytime I see the word burn, that's evidence of a chemical change, and that's another neat tip there. If the reaction is not reversible, if I cannot go backwards, it's a chemical change. If I can go backwards, for the most part, then I have a physical change. Silver tarnishing. This word here, tarnishing, that's example of a chemical change. So the silver reacts with the oxygen in the air. So the chemical symbol for silver is Ag. It reacts with oxygen in the air and forms silver oxide. Silver oxide just looks like a very dark, almost greenish coating on silverware or any silver item on jewelry. Next we have popsicle melting. If the popsicle melts, it's going from a solid to a liquid, but does it still retain the same properties? Can I take that liquid and freeze it and go back to the solid form? I can. Popsicle melting is an example of a physical change. So what we've noticed so far is that if I change states of matter from solid to liquid to gas, this is equal to a physical change. If I have a reaction that's not reversible, I'll just put not reverse. This is equal to a chemical change. I would definitely add those to my definitions. Grinding coffee beans. I've gone from big pieces of coffee beans to smaller pieces of coffee beans, but they're still coffee beans. Physical or chemical? Physical. And last, burning kerosene. That kerosene burns. It turns into fuel, and heat is given off. Burning is a key word for chemical. A few quick tips for evidence of a chemical reaction. There are 3 I want you to write down. The products have very different properties than the reactants. I gave you the example of the hydrogen gas and the oxygen gas chemically combining to make water. And then I said, would you be okay if I put a mask of water over your face? And hopefully all of you said no. The products have very different properties than the reactants. So properties of water are very different than the properties of oxygen gas or hydrogen gas, and vice versa. What if I were to start with water here and I use some electrolysis to separate the water molecules into hydrogen gas and oxygen gas? The reactants have very different properties within the products. It works both ways. Evidence number 2, and most students tend to forget this, especially on test day. A precipitate, make sure you have this word written down. A precipitate is formed. A precipitate, if you are not familiar with the word precipitate, write this word down as well. A solid formed during the chemical reaction of two liquids. I'm going to take two liquids. As soon as those two liquids touch, they form a solid in solution. So before, I have two containers here, and you see they both have liquids. And when these two liquids combine, they form a solid. There's a yellow solid here. Now what may be a little bit confusing from this picture, I do start out with two liquids and I get a solid, but it doesn't form just a solid alone. I'm going to have a liquid, and then at the bottom, there's my precipitate, or the solid that forms. So I pour two liquids into this container, and as a result, I still have some liquid, but I form a solid at the bottom. That solid is my precipitate. And last but not least is temperature change. If my temperature changes from hot to cold or cold to hot in either direction, it means that energy was either used or energy was released. And as a result, we were breaking or forming new bonds. So a temperature change is evidence of a chemical reaction. When I break or form new bonds, it means I'm rearranging those atoms and forming a different substance with different properties. I would like for you to be able to do the following by the end of this lesson. Can you define the vocabulary terms found at the beginning of the lesson? Atom, molecule, element, compound. Can you use words to describe these terms? Can you draw a picture to describe these terms? And can you identify a picture and tell me which vocabulary word it is? Number 2. Differentiate between physical and chemical properties. Can you easily tell me the definition of both and differentiate between these two properties? Number 3, differentiate between intensive and extensive properties. These are physical properties. Can you tell me the difference between the two? Which one depends on mass? Which one does not depend on mass? Can you give me examples of each? And number 4, can you list evidence of a chemical reaction? If you're still rusty on any of these 4 tasks, I want you to go back and review the content before you come to class tomorrow.